Hello and welcome you all to the 10th lecture of the Electroweak Interactions to the Standard Model Particle Physics course. And in this lecture today, we are going to look into the antiparticle solution of the Dirac equation. Now, you all recall that we did the particle-like solution for the Dirac equation in very detail, and basically we obtained 4 solutions. The 4 solutions were like this, that you had 2 positive energy solutions, 2 negative energy solutions, and each of these 2 positive energy and negative energy solutions was representing one like spin up and one spin down case, right? So this was what we actually saw. Now let's see what happens to the antiparticle solution, and by finishing this lecture we will be able to relate the particle like solutions and the antiparticle like solutions by a transformation, and that will be very interesting. Okay, so let's get started. All right, so you remember that we ended the lecture by saying that how this antiparticle solutions should look like, and we argued that the antiparticle solutions should be something like, psi xt v e comma p. So you remember that u e comma p or v e comma p, this actually contains the spinorial part of the solution, which actually says that this is just not a complex number, rather it's a column matrix with 4 different entries. But the wave function part, or rather the phase space part, will be actually having a minus sign. So this will be minus I p dot x minus et. Now this is exactly the other way round from that of the particle like solution. So the sign is here opposite compared to the particle like solution, and this VEP is essentially the antiparticle spinor. Now, why this solution is legitimate for antiparticle like solution? Now, because you can see that when you do this operate like I del del t on this psi, what essentially this is going to give you? This is going to give you minus of E psi. So, this basically gives you the negative energy solution, which is the characteristic of antiparticle. Similarly, if you take the momentum operator and act on this wave function like minus I del psi, what you are going to get? You are actually going to get minus of p psi, which is quite evident, and that is basically negative momentum solution. So, basically then you can claim that this test solution that you started with, psi xt is equal to V e p e to the power minus I p dot x minus E t is indeed caters to negative energy and negative momentum solution characterizing antiparticles. Now let's get back to the Dirac equation. So the Dirac equation was I gamma mu del mu minus m psi is equal to 0. So let's substitute the template solution, the antiparticle solution that we obtained in this Dirac equation, and see what we are going to get. Well, of course we are going to get minus gamma 0 E plus gamma 1 px plus gamma 2 py plus gamma 3 pz minus m v e p is equal to 0. So now this is what? This is essentially gamma mu p mu plus m v e p is equal to 0. Now this is something interesting. You can remember, or rather you can compare this antiparticle like solution. So VEP, the antiparticle spinor, basically needs to solve this equation gamma mu p mu plus m v e p equal to 0. Now you can compare it with the particle like solution or the particle like spinor UEP, and that was solving the equation like gamma mu p mu minus m UEP equal to 0. Okay. So now let's do the first thing, the easier thing first, which is to look for the p equal to 0 solution. So for p equal to 0 solution, this above equation, this equation basically turns into gamma 0 e plus m v e comma 0 equal to 0. Now if you put the form of gamma 0, which is 1 1 minus 1 minus 1 4 cross 4 matrix, so this equation turns into e into this guy v e 0 is equal to minus m v e 0, where minus m is on the right hand side. Now clearly if I put V E0, so once again I can have 4 independent solutions for this antiparticle spinor, which is like 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 and 0 0 0 1, right. So there are 4 possibilities. Now the question is, suppose you take V E comma 0 equal to 1 0 0 0, just like the particle spinor that we did. Put this back in this equation and see what is the kind of value of E that we are getting, what is the eigenvalue, and you can easily calculate and find out that this energy is nothing but E is equal to minus m. So this basically means that unlike the previous particle-like solution, the spinors 1 0 0 0 and 0 1 0 0 are going to give you E is equal to minus m, which are negative energy solutions, right. These are negative energy solutions, or rather these are negative energy antiparticle solutions, if you may say. Or on the other hand, V E0 0 0 1 0 0 0 0 1, this is going to give you, if you put here, this is going to give you E is equal to plus m for p tending to 0. So that basically means that these are going to give you positive energy antiparticle solutions. So now we are also getting 4 solutions in this antiparticle case also, 2 positive energy and 2 negative energy solutions. But remember that the nomenclature, or rather the way the matrix, the eigenstates that behaves, that is changed. This 1 0 0 0 0 1 0 0, that is giving me negative energy solutions, negative energy antiparticle solutions, and 0 0 1 0 and 0 0 0 1, these are giving me positive energy antiparticle solutions. Now let us do this case for p not equal to 0. Once again what we are going to do, that we are going to, like the previous analysis, the way that we did it for the particle-like case, we are going to choose the 2 component spinors VA and VB to constitute the full spinor, the Dirac's antiparticle spinor V. So VA and VB are the 2 component spinors with it has 2 entries V like this, and similarly for VB. Now let us put it back into the Dirac equation. The Dirac equation now for the antiparticle spinor will solve gamma mu p mu plus m v e b equal to 0. So gamma mu p mu plus m v a v b equal to 0. Let us remember that what was gamma 0? Gamma 0 was 1 0 0 minus I. What was gamma I? This was actually 0 minus sigma I 0, right. So let us first write this equation. This is actually gamma 0 E minus gamma 1 p x minus gamma 2 p y minus gamma 3 p z plus m into V A V B equal to 0, right. So the gamma 0 E part will be 1 0 0 minus I E, and this minus of gamma 1. So I think I made a mistake of the sign here. This is plus sigma I and minus sigma I. So therefore this is minus of 0 sigma dot p minus sigma dot p 0. So this is this part plus m. This is the diagonal matrix I 0 0 I V A V B equal to 0. Now if you rearrange all these terms, put together this part, this will be E plus m I. This part will be minus of sigma dot p. This term is plus sigma dot p minus of E minus m I V A V B equal to 0. So now if you do this matrix multiplication, what we are going to get? We are going to get E plus m I V A minus sigma dot p V B equal to 0, and then the second term is sigma dot p into V A minus E minus m I V B equal to 0. Therefore what it says that I can have V A is equal to
sigma dot p by E plus m into Vb, because there is an identity matrix and I can easily rearrange this matrix equation in this particular format. On the other hand, from the second equation, what we are going to get, I am going to get Vb in terms of Va. So, I am saying that from this equation it looks like that this, let us choose this color. So, the Vb is going to be sigma dot p by E minus m V A, correct? So, this is what we have gotten. All right. Now, what we are going to do, that now we are going to take two test solutions for VA. So, let us take simplest orthogonal form of VA will be 1 0 and 0 1, because these are two component spinors, right. So, let us take these two solutions and see what exactly VB are and correspondingly what will be the antiparticle spinor solution. So, this is a simple exercise. So, Vb is sigma dot p by E minus m Va from this equation, and once you choose the template solution. So, what was sigma dot p? This is something that we calculated before. If you remember, this will once again come from the explicit form of the Pauli spin matrices. So, this is a 2 cross 2 matrix. So, the sigma dot p will be Pz minus Pz here, this will be Px minus Ipy, and this will be Px plus Ipy, right. So, therefore, for Va is equal to 1 0, the Vb will be simply the matrix multiplication of 1 by E minus m Pz Px minus Ipy, Px plus Ipy minus Pz multiplied 1 0. Let us do the matrix multiplication. So, this will turn into Pz by E minus m, and what will be this term? This will be Px plus Ipy by E minus m. So, therefore, let us call this full spinor matrix V4. There is a reason why I call it V4, that I will explain you later. But what will be this thing? This will have Va on above, Vb on the below. What was the choice of Va in this case? This was 1 0, and this is Pz by E minus m, and this is Px plus Ipy by E minus m. Let us take the p tending to 0 limit. What kind of eigenstate that we are getting? This is 1 0 0 0. Now, can you tell me what exactly will be the eigenvalue of this kind of antiparticle spinor? You remember that for 1 0 0 0 we already derived that this is going to give me the negative energy solution, or rather negative energy antiparticle solution. So, this is going to give me negative energy antiparticle solution. Excellent. Let us do the next job. For Va is equal to 0 1. So, then we do the same thing, sigma dot p by E minus m Vb, Va is equal to Vb. So, therefore, do this matrix multiplication. This is going to give you Px minus Ipy here, and this will be minus Pz here. So, now put everything together, and this is going to be 0 1, the full spinor is V3, let us call it V3, this will be 0 1 Px minus Ipy by E minus m, and this is minus Pz by E minus m. Once again, if I take the p tending to 0 limit, what kind of eigenstate that it goes to? This is simply 0 1 0 0. Once again, you remember from this exercise that we did that 0 1 0 0 also gives you the negative energy solution for the antiparticles. So, this is also the giving you the negative energy antiparticle solution. Excellent. Now, we will have the other solutions obtained from the template choices of VB. So, I can choose VB once again 1 0 and 0 1, and I will then resort to this other equation which says that if I know VB, I can find VA by having this sigma dot P by E plus M into VB, right. So, let us use that equation. So, this is VA is equal to sigma dot P by E plus M into VB. If you use explicitly what is the form of sigma dot P, this is what exactly it turns out to be, which is 1 by E plus M Pz Px minus Ipy Px plus Ipy minus Pz Vb. Let us choose the specific form of Vb, say for example 1 0, do the matrix multiplication like this one, and this turns out to be Va is equal to 1 by E plus M Pz Px plus Ipy, right. Now, if I put everything together into the matrix form, and then what is the eigenstate that we are going to get? Remember, Va comes above, so this is going to be Pz by E plus M Px plus Ipy by E plus M, and this was 1 and 0, which was the choice of Vb. Now, for the p tending to 0 limit, what was the solution that we are getting? This is 0, 0, 1 and 0, and I call this solution as V2 EP. And once again, from the previous analogy, for the momentum 0 momentum case, we know that 0 0 1 0 is going to give me positive energy solution with E is equal to plus square root of p square plus m square, and this also corresponds to spin down. Now, why this is spin down, I am going to come up in a moment. Now, let us do the other part, which is Vb equal to 0 1, and once again let us put that Va is equal to 1 by E plus M sigma dot P Vb, put this matrix value 0 1, do the matrix multiplication, and here we go. This is exactly how the form looks like, that this is 1 by E plus M Px minus Ipy minus Pz. So, if I now put the value of Vb together, I get the full spinor, and this is going to look like Px minus Ipy by E plus M minus Pz by E plus M, and this is 0 and 1. If you take the p tending to 0 limit, what you are going to get? You are going to get 0 0 0 1. And once again, from the exercise that we did at the beginning, we know that this corresponds to a positive energy antiparticle solution, and this will correspond to the spin up solution. Now, once again, for the antiparticle, what is spin up solution and what is spin down solution, that is something that we are going to come to. But at this moment, we are at least sure that we are going to get 4 independent antiparticle solutions V1, V2, V3 and V4, which looks like this, out of which V1 and V2, the way that we have chosen, gives you the positive energy antiparticle solutions, and V3 and V4, the way that we have chosen, gives me negative energy antiparticle solution. So, therefore, together you can argue that we have, for both particle like solutions and antiparticle like solutions, we have 8 solutions: U1, U2, U3, U4, V1, V2, V3, V4. Obviously, not all of these are independent, actually 4 of them are independent. So, it is usually more convenient to work with the positive energy solutions only. So, we say that we choose 2 positive energy particle like solutions, like 2 particle like solutions, the ones which gives me positive energy particle like solutions. Particle like solutions is of course following u into e to the power I p dot x minus E t, and those u1 and u2 are essentially, if you remember, these were the 2 eigenstates. and two antiparticle solutions which also gives you the positive energy solutions, which are V1 and V2. So, therefore, we choose to work with these four independent solutions, two particle like solutions and two antiparticle like solutions. Excellent. Which are all positive energy solutions, two positive energy particle like solutions, two negative energy antiparticle like solutions. Now, we have been long hanging around with this normalization constants which we do not know what to use. You know, you can do obtain it by the normalization, like rho is psi dagger psi, which will turn out, of course, if you put it like psi is u e to the power I p x p dot x minus E t, then it will be u1 dagger u1 or u2 dagger u2 or v1 dagger v1 or v2 dagger v2. Let us choose the u1 solution. We know exactly how the u1 solution looks like. So, rho is u1 dagger u1. Let us do the matrix multiplication, which I am not going to do. You are going to work it out, and you will find that this expression is turning out to be mod n square 2e by E plus m. Now, you remember the Lorentz invariant way of normalizing this is to say that rho, which is u1 dagger u1, has to be equal to 2e. Okay? So, if this has to be equal to 2e, then this normalization is square root of E plus m, and that is the case for all the other cases also. So, each of this n1, n2, n3, n4, these are nothing but square root of E plus m. Okay? All right. So, I am not writing for the others, but you check that the normalization is the same for all these ones. Now, I would like to come to a very important point, and this is actually the case of how the antiparticle spinors behave under different operators. Now, first thing that we already checked that, okay, so you remember the definition of psi in terms of antiparticle like spinor was V into e to the power minus I p dot x minus E t, right? Or you can say that this is V into minus I p mu x mu in the 4 momentum notation. Now, when you do this, take this Hamiltonian operator, this is I del del t of psi v. Let us put an explicit v beneath to make it sound like it is an antiparticle solution or antiparticle spinor that we are seeking the solution for. So, h psi v will be I del del t of psi v. Now, what is that? That is going to be minus E psi v. So, this is the negative sign that is coming in front of energy. Similarly, if you take the usual momentum operator, which is minus I del acting on psi v, this is going to give you minus of P psi v. So, the operators which are actually going to give you the physical energy and momentum associated with the antiparticles must have a negative sign on above on top of them. So, what we are going to do, that we are going to define the Hamiltonian operator for the antiparticle as minus I del del t. If you take this operator act on the antiparticle spinor, what we are going to get? You are going to get the positive energy eigenvalue. So, this is what exactly it should be. So, because it is getting minus E, it is sort of not giving you the physical energy and momentum. Similarly, if I take the momentum operator to be plus I del, then when I operate on psi v, this is going to give me the positive momentum solution plus p psi v. So, with therefore E p going to minus E and minus p, the orbital angular momentum L will go to minus L, because r cross p will become, because p is flipping the sign, right. So, therefore, it is going to minus L. So, for the Dirac Hamiltonian to be able to commute to the total angular momentum L plus S and to retain it to 0, we also easily understand that the spin operator which will be acting on the antiparticle also has to come with an intrinsic sign of minus S. So, the spin operator that will be acting on the antiparticle solution must also have a minus in front. So, for example, Sz of V will be minus of Sz, and we can simply define it like minus half of sigma 3 0 0 sigma 3, which is, once you put the values of sigma 3, it will turn out to be minus 1 1 minus 1 1 diagonal matrix, right. So, now if you operate this Azv with this negative sign up front, acting on the V1 spin, or say for example, which is defined as 0 0 0 1, and then what we are going to get, can you tell me? It is going to give you, if you look into the Sz matrix, this is going to give you plus half B1, right. So, this is going to give you a spin up solution. So, spin up antiparticle. Similarly, if you act Azv on the V2, then you get what? You actually look into this thing, operate this, do the matrix multiplication, you are going to get minus half V2, which is the spin down solution. So, therefore, you can clearly see that now, as the positive energy and negative energy solutions, that nomenclature, the way the matrices were, the spinors were arranged, that was changed. And similarly, with this new definition that the spin operator, when it is acting on the antiparticle spinors, must also have an extrinsic minus sign in front of it, also shifts like 0 0 0 1. This was for the particle like case, it was giving the spin down negative energy solution, right. So, but actually for the antiparticle, this is actually the spin up solution. So, similarly, Az acting on V2 is giving you minus half V2. So, this is giving you the spin down solution. So, therefore, we can come back to this nomenclature that we have U1. So, this was, both of these were the positive, all of these 4 that we chosen are the positive energy solution. U1 and U2 are the positive energy particle like solution, and V1 and V2 are the positive energy antiparticle like solution. So, for U1, this corresponds to sort of spin up state. I am going to talk a little more about the spin up and spin down nomenclature in next day lecture, because we will see that there is a bit of problem in doing so, but for the time being we are simply adhering to these nomenclatures that we have defined. And so, what we have seen that V1, unlike so this corresponds to a spin down solution, and V2 is a spin up solution. Now, one question which I would like to ask here is that whether in some way we can relate the particle spinors and antiparticle spinors by some transformation, but I think I am going to postpone that till the next lecture. So, I am going to see you soon in lecture 11, and there we are going to correlate this particle and antiparticle like spinor solutions to some extent. All right, stay tuned.